In this video, we're going to be discussing functions in more detail and different properties that some functions have. We're first going to be discussing even and odd and what type of symmetry that would entail. So for example, if a function is even, if for every number in its domain, the number negative x is also in the domain. So for every x in a graph, do a real simple sketch over here, for every x in a graph, there will also be a negative x in the graph. So f of a positive x will equal the same y value on the negative x of the graph. So in other words, you can see that this graph is going to have symmetry over the y-axis. So a function is even if and only if for every x it also has a negative x, which means it will have y-axis symmetry. A function is odd if for every number x in its domain, the number negative x is also in the domain. So this means for every x in the domain, so for this x here, the negative version of that same value, so the whole function becomes negative. So both the x and the y both become negative, means it's going to flip around the origin and thus have origin symmetry. Notice we do not discuss x-axis symmetry. The reason why we do not discuss x-axis symmetry is because if I have a graph with one point here, and if it had x-axis symmetry, the other point would be down here, the question becomes, is this a function? Well, remember the vertical line test. A vertical line, if it passes through any graph more than one time, it is not a function. So any graph that has x-axis symmetry is not a function. So therefore, we don't discuss x-axis symmetry when we're dealing with functions, because that would entail it is not a function. So we're only going to be talking about y-axis symmetry, which indicates it's an even function, origin symmetry, which indicates it's an odd function. So we have odd and even. So the theorem says a function is even if and only if its graph is symmetric with respect to the y-axis. A function is odd if and only if it's symmetric to the origin. And we just proved it by showing these little graphs over to the side. So let's look at a few examples. Let's determine even and odd functions from the graph. So we have these graphs right here. Let me pull that down a little bit. There we go. That'll work. Okay. So this graph right here, you can see it definitely has y-axis symmetry. Every point on this side is also on this side of the y-axis. Since that is true, this will have y-axis symmetry. And by definition, any function that has y-axis symmetry is even. So this is an even function. Over here, this does not have any symmetry at all. You could see that this part of the graph is not over here, so it doesn't have y-axis symmetry. It also does not have origin symmetry because this hump on this side has not been rotated 180 degrees around the origin. It is not in the fourth quadrant, so therefore this has no symmetry. But it is a function. But it does not have symmetry. This was a function. It had y-axis symmetry. This is a function because it passes the vertical line test. But is this function even or odd? If this function is even or odd, it will have some sort of symmetry. This symmetry, you can see, starts in the first quadrant And if I rotate this part of the graph in the first quadrant around the origin, it's going to end up down here in the third quadrant. This is what we call origin symmetry. And when we're dealing with functions, we call origin symmetry, meaning it is an odd function. So here's an even function, an odd function, and then a function that is neither odd, it is neither odd nor even. It is neither. To identify them algebraically, we simply just use the rules that were stated above in the rectangles. To determine if the function is even or odd, first find f of negative x and simplify. So we're first going to determine whether the graph is even first. Remember, if the graph is even, plugging in a negative x for x will equal the original. So for every positive x, there will be a negative x on the other side, creating this y-axis symmetry. So we're going to find what f of negative x is and see if that's equal to the original function. So to determine whether it is even, to test whether it is even, we see if f of negative x is equal to f of x. So we plug that in. F of negative x, we plug in a negative x here and a negative x here. So that means we have negative x to the third plus 5 times negative x. Is that equal to the original, which is x to the third plus 5x? Are those two sides equal? Well, since this is to the third power, that negative sign will stay, so this is negative x to the third. This becomes minus 5x, so it's clear that these two sides are not equal to each other. Therefore, this is not even. So now we're going to test to see whether this function might be odd. To determine whether it is odd, we use the function whether f of negative x or the negative x is equal to the negative y. So we're going to put the negative in for x and the negative outside the function and see if those two things are equal. So we ask ourselves, is f of negative x equal to negative f of x? So f of negative x we found over here already. That was negative x to the third plus 5 times negative x. And is that equal to negative in front of the whole function? So we'll put that negative in front of the function, x to the third plus 5x. Well, when I simplify this left side, this is negative x to the third. This is minus 5x. On this side, the negative gets distributed, so it's negative x to the third. This is negative 5x. And look, both sides actually do equal. So therefore, yes, we do have odd function. An odd function means that we do have origin symmetry. Let's try the one to the right. We have a function negative 4x to the third minus 1. So again, to determine whether it is even, the first thing we do is ask if f of negative x is equal to f of x. So f of negative x is going to be negative 4 times negative x to the third minus 1. Is that equal to the original function, which was negative 4x to the third minus 1? Now this negative sign is not going to disappear because it's to an odd exponent. So I'll have a negative times a negative, which actually means positive 4x to the third. And because of that, these two sides are not equal. Therefore, this function is not even. Let's see if it is odd. To determine if it is odd, we take f of negative x, which we already did. So it's 4 times negative negative 4 times negative x to the third minus 1. And we set that equal to negative of the whole function. So we put a negative outside this whole function, which is negative 4x to the third minus 1. So if I simplify the left-hand side, this negative 4 times this negative x becomes positive 4x to the third minus 1. This negative will get distributed. It becomes positive 4x to the third plus 1. So you see that the first terms match, but now I have a minus 1 on the left, a plus 1 on the right. These two sides are not equal to each other. Therefore, this function is neither even nor odd. For this last one here, let's first test whether it is even. Again, the test to determine whether it is even, test whether negative x equals x. So we plug in the negative x into the original function, so it becomes negative 2 times negative x squared minus 3. Is that equal to the original function? Well, this negative x, the negative will disappear because I'm taking it to an even power. So this becomes a positive x squared, but I have the negative 2 out in front. There you have it. This function is indeed even. Let's also test to see if it is odd. As it turns out, they cannot be both. But let's go ahead and test anyways, just to get the practice. To find out if it is odd, we'll first find f of negative x, which we already did on the left-hand side over here. So f of negative x, we take negative x and plug it in. And we see if that's equal to negative of the whole function. So we put negative on the outside of this whole function. So this becomes negative 2x squared minus 3 equals positive, because I'm distributing, 2x squared plus 3. You can see that those two signs are not equal to each other, so it is not odd. And I could have guessed that because, again, you cannot have a function that is both even and odd at the same time. It is one or the other. It could be neither, but it can't have both. So let's try this last one. A function is equal to x to the third minus 2x plus 1. So let's test to see whether it is even first. So we find f of negative x, so we plug negative x in for x. And see if that is equal to the original function, f of x. So we set it equal to the original. This is negative. This is positive. Those two sides are not equal to each other, therefore it is not even. Let's test to see whether it is odd. To see whether it is odd, we use the test that whether negative x is equal to negative of the whole function. So negative x would entail negative x to the third minus 2 times negative x plus 1. Is that equal to negative of the whole function? So is that equal to negative of the original whole function? So this becomes negative x to the third plus 2x plus 1 is equal to negative x to the third plus 2x minus 1. And you can see these two sides are not equal because we have a plus 1 on the left, a minus 1 on the right. So this is neither. So we had an odd function, even function, neither. So how do we use a graph to determine where a function is increasing, decreasing, or constant? So we have this graph here, and we're going to determine where it is increasing, decreasing, or neither. We describe the behavior of a graph in terms of its x values. We do not say this graph is increasing from this point to this point. So for example, over here, the graph, it starts off on the left-hand side. This part right here is what we call it is decreasing. So anything in red is going to be decreasing. It is decreasing between this point to this point. Then, at that point, it starts to increase. So it is increasing all the way up to this point. So anything in red would be increasing. This part of the graph is what we call it being constant. In other words, it does not increase in value y, it does decrease in value of y. It is remaining consistently constant one number. Then after that, it begins to decrease again. So at this point, it is decreasing. We always move in terms of x from smallest to biggest, so we always are moving to the right. So moving to the right, we see that it's decreasing, increasing, constant, decreasing. We never move to the left. So when we describe these, again, we do not say that the graph is increasing from -4, -2 to the point 0, 4. So we don't say it's increasing from this point to this point. We just give the x values of where it is increasing. So you can see that this green area where it is increasing from this x, which is -4, all the way up to this x, which is 0. So it is increasing in between those two x values. Now, the question is, in interval notation, do we include the endpoints? And the answer would be no. Never ever do we include the endpoints. Because this endpoint, in essence, is just a transition. This endpoint has to belong to either the decreasing side or the increasing side, but it can't belong to both. So to be fair, we say that this point is the minimum point at which the transition occurs, but is not included in either one side. The decreasing part starts at an x value of -6 and goes to an x value of -4. Then it picks up again after that, and it starts to decrease again from 3 to 6. So it is decreasing between -6 to -4, and is also decreasing from 3 to 6. Now the blue area is where it is constant. It is constant between here and here. So it is constant from an x of 0 to an x of 3. Okay? Sometimes it's best to look at these in terms of the graph itself. So I like to look at it as decreasing. You can write this down here. So from -6 to -4. Then it's increasing right after that from -4 to 0. Then right after that, it is remaining constant, starting at 0 to 3. Then right after that, it's starting back up at 3. And then it starts to decrease until it gets to 6. So you see it goes from -6 to 4, -4 to 0, 0 to 3, 3 to 6. So all of these should be a continuous collaboration of x's, never missing one of the x values. For the graph below, let's also state the intervals where it is increasing and decreasing. Okay, so starting again from the left-hand side, moving to the right, this will be the first point I get to, and this graph is increasing. Then when I get to this point, it looks to be constant. The y value does not change. It was 2 here, and it's still 2, so therefore it remained constant. Then it begins to decrease. As I move to the right, it begins to decrease. So my intervals would be increasing from this x to this x. So that's from -5 to -4. Then it is remaining constant from this x to this x, which is -4 to 1. Then it starts to decrease from this x, I should write that in red, then it starts to decrease from this x to this x. So from 1 to 4. See how there's no gaps in between these numbers? It picks right back up on the next interval. So stating these intervals, it's increasing, decreasing, or constant. It is increasing from -5 to -4. It is decreasing from 1 to 4. And it is constant from -4 to 1. State the domain and the range. Remember, the domain is a set of all possible x values. So if we look at this, x, the first place I see an x is right here, and the x is -5. So x can be any number, not here, starts at -5, and x can be any number all the way until I get to an x of 4. So the domain is going to be any number from -5 to 4. Now notice I do include the endpoints for a domain because these are actual points on the end which are included. But we don't include the endpoints when we say that it's increasing or decreasing because they're a transition point. They don't belong to either side. The range is the values of all the y's. So we start at the very bottom. We see no y until we get to this point right here. This is the lowest point where the y value is -5. And then it goes up, and the highest point we see is right here where the y value is 2. So the y can be any number from -5 to 2. State whether the graph is odd, even, or neither. Now just by looking at the graph, I can determine based on symmetry. Remember, if it has a y-axis symmetry, that means the graph is even. This does not have a y-axis symmetry because this point, -4, 2, would be over here on this side of the graph, which it is not. So it does not have y-axis symmetry, so it is not even. Also, if it has origin symmetry, that indicates it is an odd function. This graph is not odd because it doesn't have origin symmetry. That means this point 1, 2 would also be down here at -1, -2, and it is not. So this actually has neither. It is neither odd nor even. For the last page, we're going to do 2 examples of calculating what is called the rate of change. You probably notice this formula looks probably pretty similar to slope. If we recall, when talking about a linear function, if it is linear, it is a straight line. And the slope of a straight line is the change in y divided by the change in x. And that's exactly what this is saying. The average rate of change is the change in y divided by the change in x. However, some of these are not linear. Some of these graphs will look a little bit different. So for example, let me graph this first one just to give you an idea of what the graph actually looks like. Okay, so I got my calculator out and I'm going to graph what this picture would look like by putting in -x to the 3rd power plus 3x squared. And that is wrong. Sorry about that. There we go. -x to the 3rd power plus 3x squared. That looks better. Okay, so once we graph that, we'll see that the graph is going to look like this. Okay, so it comes down, goes back up, and goes down again. First of all, is this a function? Yes. Any vertical line that I try to pass through here is only going to pass through one time. No matter where I draw the vertical line, it will only hit the graph once. So it definitely is a function. Can you tell by looking at it whether it's even or odd? Well, sure, I could look at the symmetry. I could tell it is not even, because if it were even, then this hump over here would also be on this side because it would be symmetric to the y-axis. So it is not even. I can determine it's also not odd. If it were odd, this hump over here would be rotated around the origin and would be down here. So it is neither even nor odd, but it is a function. Now the rate of change, we can't really find the slope of this whole graph because the slope would be different at any particular point. If I zoom in just a little bit, if we look at just in the middle area here, you're going to notice that the slope, for example, if I drew a line between this point and this point, the slope in between those 2 points would be negative. If I found the slope between this point and this point, my slope would be positive. If I found the slope in between this point and this point, my slope would be horizontal, which would mean it has a slope of 0. So we don't call it slope when the graph is actually making these turns and it is not linear. So when your power is greater than 1, meaning it is not linear, meaning you have turns and twists in your graph, we don't call it slope. We call it the average rate of change between any 2 particular points. Because we have to pick 2 particular points in order to find the change in between them. And it's going to be different if we pick a different set of points. So we have to be specific on which 2 points we pick to find the slope in between them, because it will be different from any other 2 sets of points. So what we're going to do in this particular equation here is we're going to find the average rate of change between -1 to 4. So if I go back to my graph one more time, let me pull it back up. This graph right here, I want the part of the graph that's between -1 to 4. Well, here's -1. In fact, maybe I can zoom in here. So I can go from an x, I can go from -1 to 4. So I'm just going to look at that part of the graph that's between -1 and 4. And you'll see just the part of the graph that's in between -1 for x all the way to 4. And it wants me to find the average rate of change from -1, which would be this point here, all the way to this point here at 4. And the average rate of change in between there would be a line connecting those 2 points. Clearly it's negative, but we're going to find what that value would be. So over here, what we're going to do is we're going to have to find those 2 individual points. In order to find the average rate of change, we have to find 2 points. So we're looking for an x and a y. But remember, y is equal to f of x. Okay? So the first thing we're going to do is we're going to start at -1. So this point over here, let's find its y value. So when x is -1, let's find the y value. So we take f of -1 and we plug -1 into the original function. So we're going to get -1 to the third plus 3 times -1 squared. -1 to the third is -1 times another negative becomes a positive 1. -1 squared is positive 1, so that means plus 3. So this equals 4. And that looks about right. This point at -1 is about 4 high for the y. So this point is -1, 4. So my first point is going to be at -1, 4. Now let's look for my second point. My second point is going to be the point that's going to be way down here when x is 4, because that's what it wants me to use. So if x is 4, I plug that in, I find f of 4. F of 4 would be -4 to the third power plus 3 times 4 squared. That's -4 to the third power, which is 64, plus 3 times 16, which is 48. So when I add those two things together, -64 plus 48, you get -16. So I'll have another point at 4, -16. So these are going to be the 2 points that we're going to use. -1, 4, and 4, -16, which is way down here. So now we're going to connect those 2 points with a straight line. So imagine a straight line going from here down to here, and we want to find the slope of that imaginary line. So the slope between these 2 points is called the average rate of change between those 2 points. So over here, to find the average rate of change, I find f of b minus f of a over b minus a. In other words, the change in the y values over the change in the x values. It's the same thing as slope, but we call it functions instead of singular points. So we take this information and we plug it into the formula. So change in y. So I'll do negative 16 minus 4 over change in x. So it's going to be 4 minus negative 1. So it's negative 20 over 5, or an average rate of change of negative 4. And like we said before, this definitely does have a negative slope, because if you look at the slope in this direction, this would be my line, it definitely has a negative slope attached to it. Let's try one more. The average rate of change we're going to find off of this graph here. So the first thing I'm going to do, let's take a look at what that graph looks like. So we have x to the third minus 2x plus 1. So here's the graph, very similar to the last one. By looking briefly at it, it appears to obviously not be even because it does not have y-axis symmetry. It might have, no, it definitely does not have origin symmetry because this hump in the second quadrant would be over here in the fourth quadrant. So it is not odd, it is not even. Okay, so we're looking specifically between negative 1 to 1 in the x direction. So let me zoom in on this. Let's just go from negative 1 to 1 in the x direction, and let's see what's happening just between negative 1 and 1. Let me zoom in a little bit more on the y direction. Let's go from negative 2 to 2. Pull that in a little bit tighter. Okay, so at negative 1, here's my point. It's coming down, and so my slope is going to be something like in between these 2 points. It's going to be negative again. So you can see that that graph is going to have a negative slope. So looking at this, the first thing I need to do again is find those 2 points. So I'm going to again make a table to find those 2 points. So I plug in an x starting at negative 1, and I find what would that be in the function. So I plug in negative 1, and that would be to the third power, minus 2 times negative 1 plus 1. So this is equal to negative 1 plus 2 plus 1, which is 2. So I have a point at negative 1, 2. And looking at the graph, that seems to be about right, negative 1, and here's my point right up here at negative 1, 2. Then we find another point. This time we want to use, as my right side boundary, we're going to use x as 1. So we're going to plug in positive 1 into the function. So when we plug in positive 1, we get 1 to the third power minus 2 times 1 plus 1. So it's 1 minus 2 plus 1, which is 0. So my other point is going to be located at 1, 0, and that makes sense because 1, 0, there's my point on my graph. So we're going to use these 2 points in the slope equation, but again, we call it average rate of change. So average rate of change is going to be the function evaluated at one point minus the function evaluated at the other point divided by the difference of those points. In other words, it's change in y over change in x, just like slope. So change in y, I subtract these 2 y coordinates, so 0 minus 2, over 1 minus negative 1. So I get 0 minus 2, which is negative 2, over 2, which is negative 1. So the average rate of change for this graph is negative 1. And by looking at the graph, that makes sense. It is definitely a negative slope between those 2 points.